To push a 4 million-pound space shuttle high into orbit requires a massive, incredibly violent release of energy. That same rapid release of energy drives the vibrant, controlled explosions of a city's fireworks display. That exact same mechanism can be seen chewing through the metal of an old car over a period of years. Despite differences in speed, heat, and scale, these three events share the same chemical engine, a redox reaction, or Tindak-Baulis redox, where the processes of oxidation and reduction happen at the exact same time. A Form 5 chemistry student must move past simple observation to prove exactly how this invisible chemical exchange occurs. Chemists use 4 specific definitions to track that process. The oldest definition tracks the physical movement of oxygen atoms. Oxidation happens when a reactant gains oxygen, while reduction happens when a reactant loses it. This equation shows magnesium reacting with carbon dioxide. As the reaction plays out, oxygen migrates away from carbon, attaching to magnesium. Carbon dioxide supplies oxygen, acting as the oxidizing agent. Magnesium accepts the oxygen, becoming the reducing agent. The second definition swaps out oxygen for hydrogen, but the rules are reversed. Here, oxidation is the loss of hydrogen, while reduction is the gain of hydrogen. In this reaction between hydrogen sulfide and chlorine, the hydrogen leaves the sulfur, which is oxidation, and binds to the chlorine, which is reduction. Tracking physical atoms is an intuitive starting point, but the method fails to explain reactions where neither oxygen nor hydrogen is present. This leads to the third definition, electron transfer. Chemists use the mnemonic oil rig to remember that oxidation is loss of electrons and reduction is gain of electrons. Returning to our magnesium combustion, we can split the reaction into 2 half equations. This breakdown shows the magnesium atom releasing 2 electrons, while the oxygen molecule accepts them. To track these exchanges in complex compounds, chemists use the oxidation number, or number pengoxidon. This mathematical system defines oxidation as an increase in value and reduction as a decrease. Assigning these numbers rely on a few fundamental rules. Pure elements always start at 0. A monoatomic ion's number matches its electrical charge, and in any neutral compound, the sum of all oxidation numbers must equal 0. This math tracks the flow of electrons, but we still need a universal ruler to measure which element pulls or pushes those electrons with the most force. That ruler is the standard electrode potential, or Kuopion electrode PIY. Represented as E0, it measures an element's exact electron pulling strength. Measurement requires a 0 point. This standard hydrogen electrode is assigned an E0 value of exactly 0 volts. This is only valid under standard conditions: ion concentration of 1.0 mole per cubic decimeter, gas pressure of 1 atmosphere, and temperature of 25 degrees Celsius. By establishing this fixed baseline, chemists created a universal framework to predict the outcome of any chemical pairing. This table compiles E0 measurements, ranking elements by potential. Negative values indicate a strong tendency to release electrons, acting as powerful reducing agents. Conversely, positive values indicate a strong tendency to accept electrons, identifying the strongest oxidizing agents. The table functions as a predictive cheat sheet, revealing exactly which atom will win the tug of war for electrons in any given scenario. Whether tracking physical atoms, applying oil rig, or calculating an oxidation number, you are always measuring the same simultaneous redox process. Memorize the standard conditions and E0 table rules now, as this logic governs the rest of the Form 5 curriculum. Mastering redox equilibrium provides the tools to decode the chemical engine behind these reactions and predict their outcomes with mathematical precision.